Look at a modern concrete dam holding back millions of gallons of water. It's a massive structural feat, designed to restrain the reservoir's physical pressure. Maintaining the integrity of this barrier requires analyzing the microscopic behavior of the liquid itself. When water moves along a solid surface, like the face of a dam, it does not slide forward as a single uniform block. This velocity profile shows that the microscopic layer of water physically touching the boundary essentially grips it, coming to a complete stop. Each subsequent layer above it slides past at an increasing speed. That internal friction between the sliding layers is known as viscosity. It acts as a resistance to flow, creating the drag forces that engineers must calculate when designing intake pipes or spillways. Different fluids resist this internal sliding in distinct ways when subjected to physical stress. We plot velocity gradient against shear stress. An ideal solid tracks the vertical axis, while an ideal fluid tracks the horizontal. Water is a Newtonian fluid, plotting a straight diagonal line. Non-Newtonian fluids curve, and ideal plastics require a force threshold before flowing. Because water is a predictable Newtonian fluid, engineers can use proportional stress values to calculate the forces acting on macro-scale structural designs. When water is held entirely still, the engineering focus shifts from sliding layers to the physical weight of static volume. On a perfectly vertical wall, the center of pressure, where the total fluid force concentrates, is located exactly 2/3 of the way down the depth of the water. Modern dams and sluice gates use structural curves to handle massive loads, which prevents the use of simple flat surface pressure equations. To solve for these shapes, engineers break the total force into components, a horizontal push and the downward vertical weight of the fluid resting on the curve. Combining these two vectors reveals the resultant force, the total physical load impacting the structure at a specific angle. Calculating these multi-directional vectors allow engineers to design curved dam faces that handle the specific, localized weight of static water. Fluid dynamics also dictate how liquids behave when they are transported inside moving, accelerating containers. In a stationary tank, a liquid rests with a flat, perfectly horizontal free surface. When the tank accelerates to the right, the fluid's inertia causes it to resist the motion, surging and piling up against the rear wall. Under constant acceleration, the sloshing stops, and the liquid locks into a state called relative equilibrium, forming a tilted surface at a specific angle. Calculating this slosh angle allows engineers to design transport vehicles that remain stable during rapid changes in velocity. Beyond static volumes, civil engineers use fluid kinematics to analyze the continuous flow of water through pipes and channels. Flow analysis relies on the principle of continuity. In a closed system, the volume of water entering must equal the volume exiting. When a channel splits, the velocity and volume adjust automatically. The total flow entering the system will always equal the combined flow rate of the resulting branches. Engineers map these continuous flow dynamics across three-dimensional space to account for variances in every direction. By analyzing a 3D differential fluid element, they can plot distinct velocity components along the x, y, and z axes, tracking how the fluid moves and deforms simultaneously. By tracking everything from shear stress to 3D kinematics, engineers translate fluid behavior into predictable values used to design modern water infrastructure.